my lab. I want you to pay a lot of attention to what goes on. This is a very special occasion. This is an occasion where we will make a lot of observations and do a lot of different experiments. Of course, when we do experiments, we have to obey all the safety regulations. And of course, if you don't pay attention, you might miss out on what goes on. For example, did you miss out on that, or what? Were you paying attention to that? Okay, what I'd like you to do now is to look at this assembly where I have a copper tent that's sitting on top of a piece of what we call transite, and underneath it there is a burner. I'm going to light the burner. And heat the copper. Now, I want you to pay close attention to any changes that might be taking place. This is a reaction where we're taking ordinary copper, but in this shape, and we're heating it. And as we heat the copper, we'll be on the lookout for some changes, because a change, if you look now, you see that a different coloration has been acquired by the copper. The hot copper is reacting with oxygen that's in the air, forming a layer of carbon dioxide. And you see the characteristic metallic color of copper is no longer obvious. And as we heat this more, we see that copper oxide is formed, and the hot copper is combining with oxygen from the air. So what I'm going to do next is turn this off completely, and I'm going to use hydrogen gas. Hydrogen gas out of this cylinder flowing through this funnel to bathe the entire copper oxide piece with hydrogen gas. And you see hydrogen gas combines with the oxide. There is copper oxide. There's copper oxide. Copper. And we'll turn this off. Now remember, hydrogen was very, very combustible. There are no flames around here, and we will not use flames. We'll let this cool off now, and you see the characteristic color of copper oxide comes back. This empty can has some water in it already. It's open, has some water. I'm going to heat it, like so. What happens when we heat the water? The water vapor escapes from the opening. You can see it coming up, okay? And now watch very carefully when I take this can and I flip it over into this beaker. It has water in it, okay? Here we go. You see the can collapse. This is an experiment that you can try to do at home if you want to, but be very careful while you're doing it. Let's take a quick look at this experiment in slow motion. Let's see what we see when we have the slow motion feature. There it is. I'm turning it over, putting it in, and it's going to collapse when it hits the water. There it is. Now the next experiment we're going to do is an experiment where we are going to use a very cold liquid. Whoops. This liquid is called liquid nitrogen. Its temperature is minus 196 degrees Celsius. And I'm going to show you a little bit of liquid nitrogen. There it is. You see, what's the stuff that you see coming off the top here? It's condensed water vapor. That's what it is. We're going to take this helium-filled balloon, and we're going to add liquid nitrogen to the balloon, and we'll see what happens. Well, some of you are covering your ears. Why are you covering your ears? Because you learned from experience that something I do with balloons might cause them to explode, right? But look what's happening to this one. You see what's happened to the balloon? It has collapsed, showing us the effect of cold temperature on the movement of the helium atoms that are inside the balloon. And as the balloon warms up, of course, it then goes all the way up to the ceiling. Well, what we're going to do next is a series of experiments with this cold liquid, which is liquid nitrogen, which we keep, by the way, in these containers that we call, we call them thermos bottles. In science, we call them Dewar flasks. Here's one where I'm going to add the liquid. You see it boils over. And what I'm going to do next is take a copper coil, and I'm going to connect this copper coil to a source of oxygen gas out of this gas cylinder. And I'm going to submerge the copper coil in the cold temperature bath and then allow the gas to pass through. You can hear the gas coming through now. Whoops, I had too much. Be careful about this. There we go. And we need to add some liquid nitrogen to keep the temperature cold. And you see what is happening to this piece of Tygon tubing. It's become stiff. In fact, I let go of it. And there is a liquid that's coming down, which I will collect in this large test tube. This liquid has its own characteristic color, which is light blue, and this is liquid oxygen. We are now liquefying oxygen. And what we're going to do is do some experiments with liquid oxygen as well as with liquid nitrogen. I'm going to save this now, put it in here, take this out, and turn off the gas. And I'm going to take now this powerful magnet, this horn gap magnet. I'm going to show you how powerful it is. I take my pocket knife and I put it here, and you see, you really have to pull it to get it out. I take some liquid nitrogen and add the liquid nitrogen between the poles of the magnet, and the liquid nitrogen passes through. If I take the liquid oxygen and add that, you see it's held between the gaps, between the gap of the magnet, in the gap between the poles until it evaporates, showing us that liquid oxygen has magnetic properties. You like this? This is... I have a little more here, so I'll show you whatever I have left here. It stays there until it completely evaporates. It warms up and evaporates. Again, showing us that liquid nitrogen does not have magnetic properties, but liquid oxygen does.
What's so large you need a big container to store it, but so small that it can fit in a beaker? Stay with us. The answer's coming up.
I will go on now to this end, and we will look at another experiment. This experiment we're going to do rather carefully on this black top, where we take a small number, very few crystals, we put them on the table like that, and then we're going to take a liquid out of this flask and pour it on top of the crystals. It looks like magic, doesn't it? It looks like magic, but it really isn't magic. In science, we understand what's going on, and when we don't, we try to understand it. That's why we ask questions. This is the crystallization of a substance we call sodium acetate out of a supersaturated solution of sodium acetate. I have a little more here, so let me add some more and see what happens. Okay? see how tall I can make this column without its falling. It's pretty good, huh? Yeah. Okay, so this is the crystallization of a sodium acetate coming out of a supersaturated solution of sodium acetate. Now, the next experiment I'm going to do is one that I actually want to do this experiment over here, so we can see it a little bit better, and I have more room to do it over here. This experiment we'll do in this large beaker. It has a volume of 500 milliliters. And what we'll do is out of this plastic bottle add a liquid. What does it look like? Well, it looks kind of syrupy, right? But it looks like honey, but it really isn't. We add another liquid. And what we have to do next is mix those two liquids together. You know, for a chemical reaction to take place, you have to mix the chemicals. And sometimes the reaction takes place very, very fast, as we saw in the explosion reactions. And sometimes you just have to wait until something happens. Sometimes you have to wait a long time before anything happens. You see that there is a color change now. This color change suggests to us or indicates to us that a chemical reaction is actually taking place. And the more I stir it, the more tired I get. So maybe I'll just stop stirring and see what happens. Whoops, this thing is coming. Uh-oh. We have a little problem here. We're making a mess is what we're doing. And it looks like this reaction is really out of control, but in fact it isn't. This is a reaction whereby we form a substance called a polymer. This actually is polyurethane foam. And you can see it just foaming out, and it looks like, what shape does it look like now? Looks like a bell, that's right, yeah. And I can tell you that it feels a bit warm here, telling us that this reaction releases energy in the form of heat. I can also, let's tap this and see. You see it's getting kind of rigid. So this is a rigid foam. This is polyurethane foam, which is part of a very important class of chemicals that affect our daily lives called polymers. Now we'll do another experiment using a different polymer. We'll do this experiment. Let's go do this experiment right next to the other one. We'll do this experiment using this polymer that everyone knows about. What's this polymer? This is, I know you said it's styrofoam, but it's not really styrofoam. It's polystyrene, that's what it is. What we're going to do is add a clear and colorless liquid to this cup, which, by the way, is a good insulator, just like polyurethane foam is a good insulator. I will see what happens. Oops. Bottom fell out, so let it drop down there. And we stir this. And it looks like the styrofoam cup it looks like the styrofoam cup is dissolving. Actually, it's not dissolving. All that we have done is added some acetone to it, and we caused the cup to collapse. All we've done is destroy the structural features of the foam, which is in the polystyrene. You can use these packing peanuts, which, by the way, are also made up of polystyrene, to do the same thing. So I'm going to take a whole bunch of these and try to put them in like this as fast as I can. I'm going to just dump them in there. And you see, they too collapse. They're not dissolving. The styrofoam or the polystyrene is still down there. And you see, in science, especially in chemistry, if you know what you're doing, you can make certain things appear and you can make certain other things disappear. We'll go on now and do an experiment using this clear and colorless liquid, which is water. I'm going to add to it a couple of drops of food coloring just to enhance the visibility a little bit. And stir this up. Then I'm going to take a polymer, which is a white powder. I'm going to take this polymer and add it to this beaker like so. This is a 1 liter tall form beaker. And then I'll take the colored water and add it to this beaker. We'll see what happens. And now turn it back. Now this polymer is a super absorbent of water. It absorbs many times its volume, the liquid that we have used here. It has a lot of practical applications, and all of you, I think, know about one such application. It is used in what? In diapers. It's used in diapers exactly. All right. What we're going to do now is look at an experiment where we mix a clear and colorless liquid with a clear and colored liquid in this glass assembly that is in the shape of a spiral. We'll do this experiment in the dark. So we'll turn the lights off and mix those two together. Here we go. With the lights on, this is an example of what we call chemiluminescence. Chemiluminescence is a phenomenon whereby energy is released in the form of light, but not in the form of heat. If I touch this, I will tell you the temperature is still the room temperature. Chemiluminescence is a phenomenon that I think most of us are familiar with in observing fireflies. The firefly has in it the bioluminescence phenomenon. That's because the reaction is taking place inside a living organism. This tube has 2 rubber stoppers at both ends. What I'm going to do is step up here. I'm going to light a match. I'm going to take the top rubber stopper off and drop the lit match in there. And we're going to do this experiment in the dark. No, I haven't disappeared. I'm still here. That was another example of chemiluminescence, except that that reaction released energy also in the form of sound, right? And if you look closely at the tube, you can see that the tube has some yellow coloration to it. That's because sulfur, which is one of the products of this reaction, deposited on the inside of the tube. Well, let's take a quick look at the same reaction in slow motion now. Let's see if we can learn some additional information about it. You won't hear the sound. There's the match. I'm dropping the match. There's the flame. You see I'm trying to get out of the way. What we like to do, you like that?
Coming up, a chemical alarm clock. But first, do you know how Christmas ornaments are made? We'll show you, so stay with us.
What we'll do next is look at a large round bottom flask, which is empty. It's got a rubber stopper on top. I'm going to add a clear and colorless liquid out of this graduate cylinder. And then add a clear and colorless liquid out of this flask. And then put the stopper on and mix. Because for a chemical reaction to take place, we have to mix the reagents together. And we'll watch and see what happens. Are there any changes that you can see? Huh? You're shaking your head. What do you see? What color do you see? Well, let's see. If we mix them like this, and we shake them just right, now what do you see? Black. Black, you say? Yeah, it's kind of black, but what else do you see? Silver, you see. My goodness. I'll tell you what I see. I see myself in here. It looks like a mirror. It is a mirror. In fact, that's what we've done now. We have made a very special Christmas ornament. You like that? Let's now look at this set of beakers where we have 2 rows of beakers, 6 in each row. What I'm going to do is mix the content of the back row beakers with the content of the front row beakers. And we'll watch and see what happens. Okay? So, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do it together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's an example of what we call a clock reaction. Actually, the alarm went off. It was a silent alarm. The alarm was the development of that color. A lot of interesting chemical changes took place before the color appeared. Now let's look at this large beaker, again a 4-liter beaker, which is empty except for air, of course, and the spinning bar that's in it. What we're going to do is mix 3 different clear and colorless liquids into this beaker. We'll see what happens. Here's the first one. And here's the second one. Anything happen? Sure, volume increased, right? And we take the third one. What's happening? Do you see anything happening? I don't see anything happening. How come I don't see anything happening? Because you say I'm not looking? Well, every time I look, the color is blue. There, the color is blue. See? Oh, you want me to look all the time? Okay. Oh, look at that. Beautiful color change. The sequence of beautiful color changes in this special reaction, the sequence is fascinating. This is what we call a chemical oscillating reaction. And this reaction is one of about 50 known such reactions. It has in it a whole bunch of different chemicals, including hydrogen peroxide, potassium iodate, manganese sulfate, sulfuric acid, potato starch, and so on. This one was discovered by 2 high school teachers in 1973, and it's named after them. It's called the Briggs-Rauscher reaction. And this reaction was studied by a lot of people for about 9 years before we began to understand the description, the mathematical description of what's actually going on in there. This is an example of how fascinating science can be. This is why we do research in science. This is why we want young people, bright young people, to go into science and to help us understand this beautiful behavior. And I hope that in this presentation I was successful in showing you how excited I am about doing science, and how much I count on all of you to someday either become a scientist or begin to appreciate what science is all about. And don't forget, no matter what you do, remember that science is fun. Thank you very much.